Greetings, in this one let's talk about some general proof regarding sequences in real analysis, and it signifies the importance, for example, in the case of proving the limits of sequences in real analysis of dealing with inequalities. So for example, if we're taking some limit and it's equal to s, we want to see whether if and that's as n approaches infinity, so that inputted natural number approaches a very high value, if the absolute value of the term, of that high value term of the sequence, will be the absolute value of that sequence value, the sequence convergent limit value. Well, let's see. So in general, there will be some epsilon that is higher than 0 in real numbers that is going to be used throughout this. And the definition for a convergent limit is there will exist some natural n, capital N, such that for every lowercase n that is higher or equal than that n, and by the way, that lowercase n is also going to be naturals, we will have that the absolute value of the difference of the sequence term and the limit value will be smaller than any epsilon, any positive epsilon. That's a real number, epsilon. Well, we can make that work also for the absolute value case. So that says that if for a very high n, the difference between s and that one term Sn that's evaluated at a very high value n beyond the nth, capital Nth term, that's some lowercase n's that are higher than that n, as we order it along natural numbers, minus the what's supposed to be the limit value to which the sequence tends, towards which the sequence converges. If that difference, and furthermore in absolute value to make sure it's in positive, as a result of this absolute value, that absolute value here, the difference between that term and the limit value, should be smaller than any real positive number epsilon. Well, we can now, just using one interesting theorem about inequalities, prove this very quickly. So whenever we get to this being smaller than epsilon, usually we put something between here and epsilon and gradually build it up. But this time we'll do something different. We have this, that basically if you subtract two numbers that are both in absolute values themselves, and it's inside the absolute value, it's smaller than if they weren't in that absolute value inside the absolute value, like this. So using this identity, we can transform this as well. So what I wrote here tells us that we can use it for this one as well. If this is in an absolute value and this is in an absolute value, then all of this is smaller than this original thing, smaller or equal to. Right? With the x and y was also smaller and equal to, by the way. And we already know that this is smaller than epsilon. Therefore, if we're dealing with a sequence that's basically the absolute value of the prescription of the terms of the initial one, its limit, if it's convergent, will also be simply the absolute value of that previous limit value.